In this video, we will analyze a network of capacitors when the capacitors are all connected in series. So I've drawn this sample circuit that has a battery with a certain EMF and three capacitors, C1, C2, and C3. The values of their capacitance are C1, C2, and C3. So if we think about what capacitance means, capacitance is the ratio of the amount of charge on the plates for a certain potential difference. So whatever potential difference is across C1, it will have a certain amount of charge on one plate. This charge will actually be a positive amount of charge. If you think about the positive terminal of the battery repelling positive charges, even though we know it's not really positive charges that are flowing, just go with it, then those positive charges will get pushed away from the battery and they'll end up just kind of piled up on this plate and they've got nowhere to go. The opposite plate on the other side will develop a negative charge. So that's supposed to be a negative Q. There we go. Then if we consider this wire, the wire began neutral. It wasn't a charged wire that we put in there. So if one end ends up negative, to balance out the charges, the other end ends up positive Q. So this plate on the left-hand side of capacitor C2 is positive, just like the left-hand plate of capacitor C1. Not only are they both positive, but they actually have exactly the same amount of charge. The right-hand plate of C2 will have the negative amount of charge, and then the same pattern is true for C3. It's a little crowded in there, but we have positive charge on the left, negative charge on the right, and these Q's are all exactly the same amount of charge. So I am going to replace my network of capacitors with a single equivalent capacitor. To correctly relate the capacitance of each of the individual capacitors to the equivalent capacitor, I'm going to need to take advantage of what I know about the voltage law, Kirchhoff's voltage law for this loop. So what I know is that the total battery EMF has to be equal to the sum of the voltage drops across all of the capacitors. So that as a charge traverses around this circuit, the amount of voltage it gains going across the battery is equal to the total amount of voltage that it loses as it completes the circuit. Then, if I rearrange this equation for capacitance, so that I solve for the voltage of a capacitor in terms of its capacitance, V equals the charge Q over the capacitance C. The EMF of the battery is equal to the potential difference across the equivalent capacitor because the positive terminal of the battery has nothing but a plain wire connecting to the upper plate of the capacitor, and the negative terminal, same thing, nothing but a plain wire to the lower plate of the capacitor. And so I can rewrite the EMF of the battery in terms of the equivalent capacitor's charge and capacitance. And then I can do the same thing for each of the potential differences from each of the capacitors. My next step in this development of the equation is to divide both sides of the equation by the charge Q. When I do this, I have to be careful to divide Q out of every single term in the equation. So on the left-hand side, when I divide by Q, Q over Q equals 1. So I have 1 over the equivalent capacitance. And then the same thing will happen for each of the individual terms. So I will end up on the right-hand side of the equation with 1 over C1 plus 1 over C2 plus 1 over C3. Sorry, that's an ugly 3. That's a little better. So I have now completed the equation that we use to get the equivalent capacitance from a network of capacitors in series.